Yesterday we continue from the yesterday we completed data movement operation, arithmetic operation, and looping and indexing operation. So data movement is a simple data move operation. Arithmetic operation is having add, subtraction, division, and multiplication. And this looping and indexed operation, here we have I explained you the copying a 11 byte character string 1 to another empty string, that is string 2. Okay, so by byte a character from string 1 is copied to string 2, right? So this program example yesterday I explained you, but let me revise this once. What happened? Initially, we initialize the index register to 0. Okay, this X is the index register. LDX stands for load index register 0. This index register is used for moving the pointer from first location to the next location, second location. Got it? Next, string 1. String 1, what is there in string 1? See here at the below, string 1 byte. So C indicates characters, hello world. So how many characters are there? 1, HELLO space WORLD. So total 11 characters are there. So the string 1 is having 11 bytes. That means 11 characters. Okay. So in the string 1, in the 0th location, that is X is having a value 0. See, the 0 is having a value 0. So directly this 0 is, see here, 0 is loaded into index register. Then this index value, X value is means a string of X, like string of array, like string 1 is like array of 0. That is first character, that is H. So H is loaded into as accumulator. Next, the same H, that means hello world, in that first letter H, that H is stored into string 2 of X. Clear? Next, what happened? TIX 11. What this TIX perform? It add a value 1 to the index register. That is X is equal to X plus 1. Okay, this 1 means it becomes 2. The 2 is going to check with 11. It will check whether it is less than this. Okay, now then what we have written? The value of X is 1 right now. Value of X is 1. So 1 is less than 11. So jump less than loop. Jump less than loop. Where is my loop? The loop is here. Got it? Loop is here. It will go back. Next, X value become 1, no? So string of 1 is E. This E value is loaded into accumulator, and that E value stored into string 2. Okay. Next, TIX. X value incremented to 2. 2 is still less than 11. So jump less than loop. It go back. So it keep doing until it reaches to D. Okay, na? So when it reaches to D, then X value became 10 at that time. Okay, once the D is copied, then it becomes 11. X value become 11. Then 11 and 11 both are equals. Okay, na? So this JLT does not occur. When 11 is equal to 11, then it come out of the loop. This is how looping works. Clear? If you understand this looping and indexing operation, next let me go to the next programming example. The programming example is as follows. Okay, see what I have to do. Program to add 2 arrays of 100 words each and store it in another array. Each word in the array is of 3 bytes. Why it is 3 bytes? Because one word comprises of 3 bytes. One word comprises of 3 bytes. So 100 words means how many bytes? 100 into 3. That means 300 bytes. Got it? So G is equal to A plus B. So what I am going to do, see here, A is an array called as alpha that I have mentioned here. B means beta. G means gamma. Okay. What I am doing here is I am taking the first element of the array, alpha array, and adding with the first element of beta array and storing that one into the first element of gamma array. Okay. Got it. This is how the operation takes place. So each time this array is having some 100 words. A is having 100 memory location, 100 word memory location. B is having 100 memory location, and gamma is having 100 memory location. Got it. So initially what I should do, I should initialize the index register. Index register value, initialize the index register value x is equal to 0. Okay, na? So LDX. Once it is done, what I'm going to do, first alpha of x. Alpha of x means first element of the alpha. That element is loaded into accumulator. Okay, na? First element is loaded into accumulator, and I'm adding the accumulator value into beta array in the first location, that means 0th location. See here, what is the index value? Index value is 1 initially. Index value is 1. Okay, now, so first element of alpha and first element of beta is added, and then store the accumulator value into the gamma. Got it? Next, what happened? I want to increment, I have to increment the index value. So index is right now index value is 1. I am performing index, I'm storing the index value into accumulator, and to the accumulator I am adding 3. So this is bit important to you. You need to understand this. Why I am incremented by 3? Why? Because we are not adding a single byte. We are adding a word, 100 word. We are adding a 100 words. So each words having 3 bytes. So that's why we have to add 3 to the each byte, each word. Okay, na? So when I add 3, then what happened? Index become 3. Earlier index was 0. Now index become 3. Okay, now next I'm comparing that index with the K300. This K300 is a memory location. It is having the value 300. So what is my index value right now? My index value is 3 right now. Okay, now 3. This 3 is compared with 300. So anyhow 3 is less than 300, then jump less than add loop. It go back to the add loop. This is a label. Again, what is the index value? Index value is 3. Okay, now then third memory location, that means second word of alpha is added with the second element of the second word of beta, and then store it into second word of gamma. Next, index value, again it need to be incremented by 3. When index value incremented by 3, index value becomes 6. Okay, na? So index value becomes 6. Once index value becomes 6, then compare 6 with the K300. What is this K300? K300 is value 300. So 6 is less than 300, then jump less than add loop. Okay, it go back to here. Like that, it keep doing until it reaches to the 100th word. Once it reaches to the 100th word, what happened? 100th word is also added. Then index value become 303. That time 303 less than 300, no, it is not possible. Then it will not execute this JLT. It will come out of the loop. This is how the looping operation works. Okay. Have a 1 minute of time. Just you glance this program. Okay, see this program. Here because of the lack of space, I written this memory locations here also. These are the memory location. K300 is a variable, index is a variable, alpha is a variable. For that, there is a memory is reserved by using a reserved word and word. Next 3 is a word, beta is a reserved word, and gamma. This is gamma. It may not be clear. Gamma is having 100 words are reserved for it. Okay, see this. Okay, shall we go for the next program? Hmm? I hope you guys are understanding this. Fifth one, input-output operation. For input-output operation, what is input? Input means data is taken from the input keyboard and store it into memory. Output means processed data inside the memory is displayed through the output device. Got it? Now, what I am doing by using this to explain this input output, to read one byte of data from the input device and copies it to output device. Okay, now output device is given here. See this. See, the input device name is F1. Input device name is F1. So when we are mentioning the device, we should use a X symbol. This is mandatory. When we are explaining about the characters, we should write C here in the place of X. But this is about the input and output device, so we must use X. Here, input device is labeled as in dev. Output device is mentioned as dev, device. Okay, so input device name is F1, output device name is OS. We have to take, by using this program, we have to take 1 byte, okay, na, data from the input device F1 and display it into output device OS. Got it? That is what we are doing. We are reading 1 byte of data. We are reading 1 byte of data from the input and we are copying it to the output device OS. Got it? So for that, the program is in this way. This is for in loop. In loop is used to read the data from the device. Out loop is used to display the data, 1 byte of data, into output device. Got it? Now, what happened here? TD. This TD stands for test device. This is also one of the instruction format. This is going to check the device. If the TD value is equal to 0, that means device is not ready. When TD value, TD in device, when we mention TD in device, input device, if it gives the value equal to 0, then the device is not ready. If it is other than that, either it is less than or maybe greater than, then it will not go inside the loop. Okay, now we'll see this. What happened when input device is checked? If the value return is equal JEQ, this is JEQ. then in loop, they go back to in loop. It was keep checking. Once the value returns is 1, then it goes to read in device. What is this read in device? RD stands for read one word of or one byte of character, one byte of data from the input device. So input device is F1. So one data is taken. I assume the value 5. That is, value some character. The character, some X is a character. It is of 1 byte. That 1 byte of character which is read by the input device is stored into the memory location data. Data, for the data 1 byte is reserved. That I have mentioned in the last line. See this. Okay. Next, once the data which is stored into the memory location data, DATA, then it will go for output device. What happened in the output device? Again TD, test the device, output device, test the device. Then if it is value returned is equal to 0, then it goes to outloop. Okay, it will be in the loop until and unless the value will not equal to 0. Once the device is ready, then the value returned by the output device will not be 0. Then it jump out of the loop and load the value or a byte, load the data byte in which is present inside the data into the load ch. When we mention load ch, automatically I told na, if you don't mention any other operator or a variable, then accumulator register A, accumulator A stands for accumulator, is the default register to take the data. That data is stored into register A, and WD. WD stands for write data. Write the data into output device. This is how a transfer of 1 byte data from the input device to the output device takes place. Got it? Now you do one thing. Just analyze this program for a moment. Okay, shall we go to the next program? What is this next program? Subroutine call. This is the last programming example in the SIC architecture. Okay. What we are going to perform here? Read out. Subroutine call to read a 100 byte record from an input device into memory. Okay, we have to read 100 byte record. 100 byte record means we have to, because this is byte, not a word, we have to read 1 byte by byte from the input device and store into the memory. What is the name of input device here? The input device is F1. Okay, na? Then where it need to be stored? Into memory. Where it need to be stored? The memory which is mentioned here as record. See, the record is a memory location. For that record is a memory location, 100 byte is reserved. F1 is the input device and 0 value is 0. K100, this is for your understanding, I have written it as a K100 is a memory location to the 100 value is stored. 100 words are stored, reserved for it. Okay. Now we'll understand this program, how this subroutine call executes. I hope you guys are seeing this. First, we all know the what is that subroutine. When the function call occurs, the transfer of control from the source main program transfer to the subprogram. Okay, na? In the same way, this is like a main program, but there is no opening braces and closing braces. Okay, when jsub read is a label, compiler goes to this read label and execute that appropriate instruction. Okay, now when jsub read executes, see, call read subroutine wherein it stores the return address in the linkage register. I already told you, when any JSub operation takes place, JSub or RSub is also there. What happened when JSub read, this particular address of this JSub instruction is stored into link register and it goes to the program, I mean subroutine. Once the execution is over, then RSub executes. When RSub, which return from this subroutine and go back to this address by using the previously stored linkage register value. That's why I mentioned here. See, call read subroutine wherein it stores the return address in linkage register. Here, when we exit from the loop, then exit from the loop, it returns to exit from the subroutine, it returns to the address stored in the linkage register. Got it? Now, so how it works? When it go to read, it initially initialize the index register x is equal to 0. Next, in the read loop, it need to read 100 byte of data and store into the memory space that is record. Test the input device TD. When it is equal, it go back to the loop. It keep waiting until the value returned by the TD is not equal to 0. When device is ready, then it goes. When device is ready, it read the input data from the input device. First data it will read from the input device, and it is stored into the accumulator. Okay, that accumulator value is stored into the record is a memory location like a array in the x location. What is x? X is 0. That means 0th location. See, store the red data into the record at the 0th address of the record. Okay. Next, it will check for TIX. TIX perform two operation. It increment the TIX. See here. This TIX is it performs the increment operation and also it will compare. Okay. This TIX increment the x value to 1 and then it will compare with 1 is less than or equal to K100. Okay, K100 is value, 100 is stored here. It is like a for I is equal to 0, I less than n, like I less than 100. It is like this. Then if it is less, the x value is less than that, then it will jump to the R loop, go back to R loop. Next, again, it will test the device. And if the device is ready, read the second letter, read the input device and store the second, read the second element from the input device and store into the record of memory location 2. That means second memory location. But according to this index, always it starts from 0 to n minus 1. That means 0 to 99. But it store into the second location. And again, it will increment the x value. It's keep incrementing like this until the value x is equal to 100. Once it is equal, then it will come out of this loop and return R sub is executed. Once R sub is executed, then it go back to the main subroutine. Okay, na? Main routine or main function. Okay, for this we used 0 is a memory location, in device, record and K100. These 4 memory locations we used. So in device is a device F1. Record is a memory space, need to store 100 bytes. 0 is a memory space, value 0 is stored. K100 is a memory space where 100 words are stored. Got it? Now you see this. See this. Try to understand this. Have a 5 minutes of time, 2 minutes of time. Understand this. If you want, you can note down this also. Okay, dear students, now we done with the SIC architecture. Next, we need to start with the SIC XC architecture. Another 2 minutes is remaining. Let me revise the concept. Okay. See, in the fourth example, we performed the addition of two array elements of having 100 words each, and adding the two arrays and store it into the another array called as gamma. That is, gamma is equal to alpha plus beta. Next, another fifth example was reading one byte of data from the input device and storing into the output device. Okay. For that, we require this TD, test device instruction. Next, subroutine here in the subroutine call, reading the 100 byte of read the data. How we will read the data? Read the data from the input device, that is keyboard or whatever it is, and store the 1 byte by byte into the record memory location record. Okay. So this clears the SIC part. So SIC is a basic version of the memory, machine architecture. Next, SIC XE, I will just give you the some instruction about this before this session ends in 1 minute. SIC XE. XE stands for extra expensive or extra equipment. That means upgraded version of SIC is called as SIC XE. This also having all the same elements like SIC. It is also having memory, register, data format, instruction format, addressing modes, instruction set, input and output also. But it is upgraded version. So earlier in SIC, memory was 2 power 15. Here SIC XE, memory is 2 power 20. In registers, in SIC, there was 5 registers were there. In SIC XE, 9 registers are there. 9 registers. Data formats also changed. In SIC, there was only one data format. But here there are 4 data formats are there. Next, data format here we represent the floating point representation. Next, instruction format. 4 instruction formats are there. Addressing mode is also 4 type of